It is recording. Okay, let's see. What do we want to do here? We want to share something. What is it we want to share? I guess that's not it. Which one is it? I can't find what I'm looking for. Oh, there it is. Sorry, my brain's not working. Okay, let's see. Yeah. Section 4.5. We still have 6, 7, 8, right? So this is kind of where we ended up here. Did we do the example of the skier? I don't remember. Where did we end up? My screen's too big here.
We did the one with a guy on a tightrope.
Oh, we did this. We did the tightrope. So we did the skier and the tightrope, and we did. Yeah, I remember. Okay, so we're good.
I remember we talked about Golden Gate Bridge too.
Okay, so what we need to do then is we need to move on here a bit. Let's move on. So in this section, we look at the kind of steps that we've been using so far to solve these kinds of problems, and it's really quite simple. You'll see here that they've got a 4-step process, it looks like, and it starts with step 1, drawing a picture. Well, actually, I guess they call that step 2. I don't know. They have too many things going on here. That's fine. So in step 1, they say identify physical principles involved and draw a careful sketch of the situation. So they draw a sketch first, and then they draw a free body diagram. So here's the sketch. We have Tarzan hanging from a rope or something. And we've drawn the picture. We've labeled some forces. We know that we have weight, we have tension, we have the force that the person is pulling down on the rope with, the tension and the rope pulling up on the person. Then we define our system of interest, and we only are going to include the forces that are acting on that system. So the tension is pulling up on the Tarzan, and weight is pulling down on Tarzan. And so that's our system of interest. We don't do the force of Tarzan pulling on the rope because the rope is not the system of interest. We throw that one out. And our free body diagram ends up looking like Tarzan, the point ape man, and the tension pulling him up and the weight pulling him down. Quite simple. And that takes us into step 2, which is the free body diagram. Now, another thing that I like to do in the free body diagram is to split up forces into components if need be. In this particular case, it's all one-dimensional. It's just all up and down. We don't have to worry about splitting into components. Whereas with the skier, we definitely had to split into components. And we even rotated our axes. Let's see if I can go back one section here. How do I go back? Here we go. That's not going to take me back. 5. So if the example of the skier, we not only did we break the weight into components, but we rotated our axes. So we had the parallel and the perpendicular axis. And then our weight had a perpendicular component and a parallel component that lined up so that we could show that the weight parallel and the friction were in one dimension, and the weight perpendicular and the normal force were in another dimension. And then our free body diagram ended up looking like this with components included. I always like to include components when I get to my free body diagram to show, really it's to show me that I've done it correctly, because my components should be in the direction of my dimensions here. My dimensions being perpendicular and parallel, and I have a perpendicular and a parallel. So it's easy to get that wrong because sometimes people will do a component for the weight that is all the way down to here and then to here, and this one obviously would not be in the right direction, so it wouldn't be correct. But just be aware of that. Let me actually draw that out because that's an important thing I just mentioned, and I just kind of mentioned it quickly. I got to find my tools. Where are my tools? Now my stupid screen is too big. There it is. Come on, tools, wake up. There we go. You guys are sitting there thinking, what is he talking about? Because you can't see my tools. But anyway, as we get into if we're doing this drawing these components on this, sometimes people will do, oh, there's one component. Oops, that's a little too long. They'll do a component like this, and then a component like this. The components of your vector should always have a 90-degree between them, and this is obviously not 90 degrees here. And also, this component that I've drawn in here is not parallel to the parallel axis, and it should be. Whereas this one is. So that's how you know that that is the correct component. When we've rotated axes, sometimes it gets a little confusing which direction these components should point. There should always be a 90-degree angle between the two components of your vector, and they should line up with your axes. So this one lines up parallel to the perpendicular axis. This one is parallel to the parallel axis. So you're good. So anyway, that's what I was meaning when I said all that stuff. So then, moving on. Does it make you dizzy when that screen just flies by? Who knows? Anyway, when we're done with our free body diagram, then the next thing is to apply Newton's second law. And when we apply Newton's second law says that the net force is equal to the mass times acceleration. And that implies that the net force in one dimension is equal to the mass times acceleration in that dimension. And they're not showing that explicitly here, but they should. That would be the net force in the x direction equals the mass times the acceleration in the x direction. And in general, it would mean that the net force in the y equals the mass times the acceleration in the y direction. Or it could be the net force in the parallel direction equals the mass times acceleration in the parallel direction, and the net force in the perpendicular direction equals mass times acceleration in the perpendicular direction. It can, mean whatever it needs to mean depending on our coordinate system. But you split it into two dimensions of Newton's second law. And then you solve these in each dimension. Now, sometimes in one of the dimensions, this mass times acceleration will be 0 because the acceleration will be 0 in that dimension. How do you know if the acceleration is 0? Well, if it's going to stay at rest for the entire time you're interested in, of course, the acceleration is equal to 0. But also, if the velocity is not going to change the whole time you're interested in it, then you can also say that the net force equals 0 because the acceleration equals 0. So two different situations there where it might equal 0. All other situations, if you don't know if it's going to be sitting still, or if you don't know if it's going to be at a constant velocity, then you have to set it equal to the mass times acceleration, and that acceleration may or may not be another variable in your problem. So once you've got those equations, then of course you're going to solve them for the things that you need to know. Sometimes in one of these, you'll have a net force. Maybe you have a force that's a push or a pull. We'll call it a push or a pull like that. And then you might have some friction, and it might be in the opposite direction of the movement or the opposite direction of the push or pull. So this one was a positive force. This one is a negative force or something like that. Whatever, and that's fine. And if this is equal to mass times acceleration, so be it. But maybe the push or pull actually has components to it. So this actually ends up having to be broken down into the force, push, pull. So this has to be the x component in that case. And this would be the force, push, or pull times maybe the cosine of theta or the sine of theta, depending on the geometry, minus the friction. And then this is equal to then the mass times acceleration in the x direction. And maybe the acceleration is going to have components. And so maybe that's not just acceleration in the x direction, it's the acceleration times the cosine of the theta of the acceleration or something. You know, you'll end up with components inside of these equations. And maybe this one, the force net in the y direction, is equal to the tension in the y direction, or maybe the normal force. Let's do the normal force just for fun. So maybe it's equal to the normal force, which is maybe a positive direction force, and then minus the weight. Well, you know, then you can break this up into the normal force minus mass times gravity, because you know that the weight is equal to mass times gravity. And then maybe that is equal to 0. Maybe there's no acceleration in that direction, in which case this would mean that the normal equals the mass times gravity. And that's great. But whatever happens in these problems, the point is that you're going to go from a sum of forces to maybe a more complete sum of forces, or a more detailed sum of forces, by plugging in components or values that you know. And then you're going to solve things that for things that you don't know about. Maybe you don't know the normal force, but you do know the mass. Now you can calculate the normal force. Maybe up here, you don't know what the friction is, but you know the pull force, and you know the angle, and you know the acceleration, and you know the mass, and you know whatever else. And you try to solve for things that you don't know using things you do know. And of course, you do want to check to make sure that it's a reasonable solution. You want to check at the end, maybe you're trying to find the acceleration of a car, and if the acceleration of the car is, you know, 5,000 meters per second squared when you're done, you might think again, because that's pretty dang fast acceleration. That's a crazy, crazy big acceleration. That means it's going 5,000 meters per second faster every second. And there's no car that has ever gone 5,000 meters per second except for one. Does anybody know which car has gone 5,000 meters per second? It's the car that Elon Musk launched on his rocket to Mars. Did you guys not see that launch last year? Raise your hand if you saw the launch of Elon Musk's car into space last year. If
I
you
saw
didn't
it.
see it, go onto YouTube and watch it. It's super funny. Most space launches, when they do a test launch, they just put like a chunk of concrete or a chunk of steel in for a test mass. But Elon Musk, being Elon Musk, decided he'd send the very first Tesla Roadster that was ever made. It was his personal Tesla Roadster. So he just put it up in the rocket and sent it off to Mars. Super funny. It even had a driver in it, and a couple of really funny jokes were in it too. Anyway, we would watch it right now, but we actually need to get done with all this stuff. So let's get done with all this stuff. When is the homework due? I can't remember.
I think it's due today at 11 now.
Okay, well,
I can look.
if that needs to be changed, we can change it. We won't have class Friday, so we can move homework till Friday for sure.
That'd be good.
Let's do that really quick just before I forget. And then we'll get started on chapter 5 on Monday. Well, we could maybe even start chapter 5 today. We'll see what time. We've probably got enough time. We'll see. All right, so then we're going to go into the last, is this the last section? Further applications, yeah, second to last section, that's fine. So other types of forces that we can deal with in Newton's laws we would consider things like drag. Drag is the same thing as friction, except instead of just being a single contact force, it's kind of it's usually what we use when we talk about fluids. It behaves a slightly different rule in general in physics, so that's why we treat it differently. And we'll see a little bit of that later on in this class as we get into fluids. But if you're going through a liquid or a gas, then we call it drag. And in this case, the drag behaves just like friction. Um, we have a force acting on this barge and another force acting on this barge, two tugboats pushing this barge in different directions. Their overall force, if you add this force to this force, you get a force that looks like this. This one plus this one equals this one, right? And the drag force will always go in the opposite direction of the movement of the barge. So it's pointing exactly in the opposite direction of the force, which is the same direction as the acceleration. So they use the force vectors to solve for the angle here, turns out, because they don't give you the angle. So the force vectors, when you add them together, you can use the inverse tangent to solve for that angle. And you can get the total force by using Pythagorean theorem. But then you have to subtract off in Newton's second law, the drag force, to get the net force, right? So this gives you the total force from these two forces. Then you add the drag force on, which is, of course, in the negative. It's a negative force, and that will give you the net force in that direction of 53.1 degrees. And they do all of the math down here. There's their Pythagorean theorem. Here's their finding the angle, and then their net force. And then once they found their net force by taking that total applied force minus the drag force, then they set that net force equal to mass times acceleration. Again, we're solving Newton's second law again here. And the thing that we're trying to solve for is the drag force. We don't actually know what the drag force is, turns out. And so we get the drag force equals the applied force minus the mass times acceleration, and we get a drag force of 7.5 times 10 to the fourth. Because apparently they told us the acceleration. I wasn't paying attention. But it's the same kind of thing. We start off with a drawing, we go to a free body diagram. In this case, in the free body diagram, they used the vectors here to solve for that angle. Once they got that angle, they could calculate the direction of the applied force, and they could use the forces to calculate also the total applied force in that direction. Then they plugged it into Newton's second law and solved for the drag force. No matter how you cut it, you can use Newton's second law to solve these problems. Here they do a problem where they have tensions at different angles. Some of you have seen this in the homework already and asked questions about it, but these are just, when you break it all down, you have a force that's pulling on the light in the direction of this cable, another force that's pulling on the light in the direction of this cable, and then of course you have the weight straight down. And this is what it looks like in kind of a SketchUp. In a free body diagram, it looks kind of like this, where you have the two tensions, but you have their components as well. So you break down the components of each vector. And then if you draw a free body diagram with just the components, then you have two tension components up, one tension component each for left and right, and then the weight down. And this one's nice because you can see that if you don't want this thing to go anywhere and you want a zero acceleration, that the weight has to equal the sum of these two tensions, and that this tension to the left has to equal this tension to the right. Otherwise, you're going to get acceleration in some direction. So that gives you some really easy equations to set up using Newton's second law. And then you solve them. When you solve them, you're going to end up with cosines and sines and things and all over the place. But in the end, they're pretty easy to solve. You're just solving for simple unknowns. This one confuses the heck out of people because we have a hard time wrapping our head around what it means to weigh ourselves. So if you're weighing yourself just on plain old ground, your weight is the gravity of the earth pulling you down. And if you're standing on the scale, which is what you do when you're weighing yourself, then the scale is pushing up on you as gravity is pulling down on you. You can essentially think as the scale is the force that the scale pushes up on you with is kind of like the normal force, right, on the scale. And if it's not going anywhere, if you're not going anywhere, then the weight down and the force up on you on the scale from the scale are equal. However, if you're in an elevator and it's moving, that changes things. It changes things. It can be quite dramatic. You can actually lose weight or gain weight in an elevator. And why is this? The reason for this is because the elevator is moving in the same dimension as your weight is and the force on the scale. And to make it move, it has to have tension in the cable above. So you have this tension in the cable above, which is pulling up on the elevator, and that that tension upward is counteracted by a let's see, where are they showing that here? I have to see which ones they're labeling which here. They have too many forces. So they have tension is the supporting cable, weight is the weight of the person. They have the weight of the scale. That one's obvious. The weight of the scale is downward here. The weight of the elevator, so that's a really big weight. That's why they put this little line in between, because this one, if you showed it its normal length, would be super long. So this arrow here is really, really long. And then they have FT, which is the force of the scale on the floor of the elevator, and FP, which is the force of the person on the scale. So FP is the force that I push down on the scale with. FT is the force that the scale pushes down on the elevator with. And that is actually a little bit bigger because it's the weight of the scale and the weight of the person, right? And so we have all these forces involved, and we're just interested in just this one right here. We're just interested in the person. What is happening there? So the two forces acting on the person are the weight down of the person and the force upward from the scale. So there's our free body diagram. And we're doing this when the elevator accelerates upward with a rate of 1.2 meters per second squared, and if the elevator is moving upward at a constant speed. So it's 1 meter per second. So we have acceleration and no acceleration. So part A is with acceleration. So the net force on our system is equal to the mass times the acceleration of our system, right? The mass of our system times the acceleration of our system. So we have the net force is equal to the force up, this force upward of the scale on the person, which is a positive Fs, and then minus the weight, and that's what we see right here, force S minus the weight. And that has to equal the mass times acceleration of the person. So the force S is the thing that we're going to read on the scale. That's actually the weight that we'll read on the dial on the scale, because that's the scale pushing on us. So we have mass times acceleration plus weight for that force if we solve this equation up here, solve Newton's equation. Well, our mass is just our mass, but we are accelerating in the elevator because they say in part A, we're going up at 1.5, it said, I think 1.2 meters per second squared upward. So that's a positive 1.2 meters per second squared right there. And then we have to add on to that our weight, which is mass times gravity, which is our mass again, times 9.8 meters per second squared. You can see here that our mass times a positive acceleration plus our mass times gravity, which is now positive because we put it on this side, we took it from this side and put it on this side, is going to make us gain weight, in other words, right? And that is true. This person is 75 kilograms. They should have a mass of about 740 newtons or so, but their mass or their weight now is 825 newtons instead of 740 newtons. So they've gained weight. And when you get in an elevator and the elevator goes up, you can feel that, especially if it's in a very fast elevator, an elevator that accelerates very quickly. You can really feel you get heavier as it starts accelerating. But what happens if there is no acceleration? Well, that same equation gets solved and the acceleration is 0. And the net force ends up being just their weight, 735 newtons. So if it's just moving at a constant speed, you get your constant weight, your normal weight. Now what happens at the top when the elevator slows down? Well, the exact opposite happens in this equation. When it slows down, the acceleration is negative, it's downward, and you get your weight minus some force there, minus some weight. So you lose weight at the top, which is nice. But then you gain it again. Here they have another example of an acceleration here. They have a soccer player. From rest, they're accelerating to 8 meters per second in 2.5 seconds. what is the average acceleration? What's the force they exert if the player's mass is 70 kilograms and air resistance is negligible? So in this case, you can use kinematics at the beginning to calculate the average acceleration, which is exactly what they do. They use a simple definition of acceleration, 3.2 meters per second squared if you do 8 by 2.5 seconds. And then for part B, they plug that acceleration into the net force equation. Where the net force is just they're pushing back on the ground because there's no force resisting them. 224 newtons of net force. So just some different ways to apply Newton's second law. Now the last part we've actually talked about a little bit. And that is the fact that there are only 4 basic forces. And here they are. Only 4. Now, of these 4, gravity is the one that we think that we're the most familiar with. Because, you know, we walk around on Earth, gravity holds us onto the Earth. But in fact, gravity is probably the one that we have the least familiarity with, both in our everyday lives and in science. So gravity happens to be the weakest of all of these forces by a far. If the strong nuclear force has a strength of 1, right here, the gravitational force has a strength of 10 to the minus 38. So gravity is an extremely weak force. And we can tell that it's an extremely weak force because the amount of force that the Earth pulls on us with is not really that much. And yet the mass of the Earth is humongous. The mass of the Earth is extremely big. And you'd think that if gravity has something to do with mass, then you have this Earth that's this huge thing. We'd feel a lot more force, but it's not that much force. We can overcome it pretty quickly. Jump around, you know, you can get over the gravitational force pretty quickly and easily. But for as weak as it is, though, you know, being so weak, it actually reaches out forever into space, and it actually reaches out further than any other force that we know of. Another strange thing about it is it's only attractive. We only can have gravitational forces that attract each other. Masses never repel each other because of gravity. They only attract each other because of gravity. And this one is, we only know this because we've observed it this way. We've never observed gravitational forces repel each other. All the other forces can repel. They can repel and attract. So we assume that it's possible that it could repel, but we've never observed it, and we have no real theoretical basis for it either. There is some thought about antimatter somehow having this part of this ability to repel, but we haven't observed that with antimatter. We actually can create antimatter and we can observe antimatter, but we've never observed it. So as far as we know, you know, gravity is only attractive, which is a big mystery. Why would all the other forces that we've observed be attractive and repulsive and not gravity? We're not sure. The other thing is most of these other forces here all obey very different laws besides just this attractive repulsive thing. These, like the electromagnetic, the weak nuclear, the strong nuclear, all of these can be explained using quantum mechanics in a fairly reasonable fashion. This one, not so much. This one is Einstein's theory of general relativity, really only. So there's some really strange things going on here. Also, we assume that all forces have some kind of a particle associated with them. Now, these particles don't necessarily have mass. They can be massless energy particles, essentially little packets of energy. Like the photon is just a packet of energy, doesn't have any mass to it. So we assume, since these other ones all have particles, these ones we've all observed, we assume that gravity has a particle. But again, we have no observation of it. We've never been able to detect this particle. So we're not actually sure if this one exists. So gravity, being the one that we think we're most familiar with, is actually the one we're least familiar with when it comes to science. Gravity is a huge but actually very tiny, mystery. And we've been observing it for a long time. It's the longest observed of all of the forces, without a doubt, but it's still the biggest mystery. If you ever discover the graviton, tell me about it, and we'll share the Nobel Prize. It'd be great. So. Or you can just tell the Nobel Prize Committee and keep it all to yourself. Anyway, so the electromagnetic force. Now this one is one that we didn't know much about before a couple hundred years ago. A couple hundred years ago, we started learning about electricity. We started to understand that there were forces pushing electrons around. Electron was the name that was given to the charges that can be moved very easily in materials. It was given to I think it was Benjamin Franklin that gave it that name. Maybe not, can't remember. But it was somebody about the same time. He certainly assigned it the negative charge, which we call it. We say that the electron has the negative charge. That was a big mistake, by the way. He should have called it the positive charge, and then our math would be a little cleaner. But anyway, so the electromagnetic force is fairly new we're fairly new in understanding anything about it, but we understand a lot more about it than we do the gravitational force, because we have been able to determine that it has a particle associated, and we'll learn more about that next semester. We also know more about its attractive and repulsive natures, and it also has an infinite distance that it can reach out, but it's much, much stronger than the gravitational force. So if the strong nuclear force is at a 1, this one's only 100 times smaller than the strong nuclear force. So it's a much bigger force. I mean, to say how much bigger the electromagnetic force is than gravitational force, you have to kind of make up words. It's like a gazillion times bigger, because there's no word for 10 to the 36 times bigger. That's just such a huge number. But this is much, much stronger than the gravitational force, but it is still quite a bit weaker than the nuclear force, the strong nuclear force. I'm going to take just a pause. I have to go and talk to somebody just for a second, so I'm going to give you a little break, and I'll be back in just a minute. Okay, I have to print something really quick, and then we'll be back to our lecture. Let's see, where did I put that thing? There we go. I don't remember where that was. There it is. Okay. All right. So then, so we've got our gravitational, we got our electromagnetic, but where does the electromagnetic show up? Well, of course, electrons are attracted to protons inside of matter. And that's what, inside of atoms, for example. Electrons repel electrons, protons repel protons. But how do we see this in our everyday lives? We see this when we touch things. In fact, you can't actually touch things. When you're touching something, you're just rubbing your electrons with the electrons of the thing that you're touching. And that's the reason when you touch something, you can't put your hand through it. Because if you could put your hand through it, then the electrons wouldn't be repelling the other electrons. Because everything has electrons kind of on the outside of it, right? And that's how it works. And So that electromagnetic repulsion is how you feel things. It's how you touch things. It's also how we electromagnetic attraction is actually how we electricity flows, or how signals in our bodies flow. It's how our muscles work. It's how the neurons flow. It's how our brain works. Just about everything biology has to do with electromagnetic force. In fact, you could really say everything in biology is electromagnetic. That's all it is. Because anything to do with chemistry, anything to do with touching forces, all these things, they're all electromagnetic. So this is actually the one that we're most familiar with, even though we don't know it, because we are touching things all the time. We're pushing things, grabbing things, pouring things, drinking things, eating things, whatever. All that is electromagnetic. Everything about it is electromagnetic. So this is the one we're most familiar with. We just didn't know it yet. The weak nuclear force is responsible for strange things that happen in the in the nucleus of atoms, usually responsible for things like radiation. And so we do see this a lot in there is this going on a lot around us, but we don't see it, I guess is the best way to say that. Radiation is happening all the time, and it's because inside the nucleus of atoms things are moving or changing, or something is happening inside there, and we don't really know exactly what's happening, but we do have a basic idea of kind of some ideas of it. But the weak nuclear force is responsible for those changes that happen in the nucleus. We'll learn more about that next semester, and then we'll learn more about all these next semester actually. Then the strong nuclear force is what holds protons together inside the nucleus. Why would protons be all squashed together in a tiny little place inside the nucleus? Well, it's the strong force that holds them together, and that strong force it actually exerts itself because of the presence of the neutrons. The neutrons are the things that provide that strong nuclear force to hold the protons together. You can't just bring two protons together and hold them there. That just can't happen. You have to have neutrons present to hold protons together. And the particle for those is the gluon. So the particle for electromagnetic is the photon, which is what light is. Light is made of photons. The weak nuclear force is all these three different particles here. And then the gluons are for strong nuclear, which is kind of funny. They called it the gluon because it's like really strong glue to hold the nucleus of an atom together. I'm not kidding. That's why they call it that. But anyway, these are the four fundamental forces, and there are no other forces as far as we know. Pretty much everything to do with life and chemistry, life, chemistry, geology, pretty much everything on Earth is this thing right here, except for a few things going on at the center of the Earth, which are more like this one here, because there's a lot of nuclear reactions in this one here going on at the center of the Earth. But pretty much everything else is electromagnetic, except for the gravity that holds us on the Earth and the gravity that holds the Earth together. So those are your four fundamental forces. Some of these forces can reach out and act at a distance, like the electromagnetic force can act without being in contact, just by acting through space or a vacuum or whatever. So can gravity. Gravity can act through a vacuum. Some of them not so much. Well, I guess all of them can do this, but it's a little bit different with some others, like the weak nuclear force and the strong nuclear force. Those ones require a certain set of circumstances and a fair amount of proximity. They have to be really close, and it may even be contact forces. We're not even sure. But this idea of reaching out, though, and exerting a force at a distance brings up the idea of force fields, where this field of possible energy, possible pulling energy or pushing energy is out there. And so it's kind of like throwing a basketball. The basketball would be like your force particle. And if you throw it to another person, you might move backward, and when they catch it, they will move backward, right? So that energy is a repulsive force energy. Well, how do you demonstrate the attractive force energy? Well, who knows? More like pulling on a bungee cord or something. But here they have a picture of I'm not sure which one I think this is Alice, but this is a detector inside of the big accelerator in CERN in Switzerland, where they're studying all these particles and forces. They're trying to figure out more about these things. Here's another experiment that they're putting into space soon. It's called LISA, and it's essentially got lasers going around through it where they can detect waves of gravity. But it turns out they actually already did it. They detected waves of gravity here on Earth. I give it to Jordan. So they're definitely trying to learn more about these things so that we can get a better fundamental understanding, but it's still in the works. And it turns out we've run out of time. Here they actually tell you they tell you more about the particles. They're called the vector bosons, and they actually have individual names, but anyway, they've got all kinds of weird names for particles once you start looking at the fundamental things of the universe, like the fundamental forces of the universe. But we'll go ahead and start chapter 5 next Monday. So go ahead and finish with chapter 4. If you have any questions before it's due, please send me emails. I'd much rather answer your emails than pay attention in the meetings that I have to go to on Friday. So enjoy your long weekend, and we'll see you next Monday.
All right. Thanks, Mr. Daly.
Thank you.